Bismillahirrahmanirrahim. Dear students, today we will discuss the complex polynomials as a product of linear factors. This topic is important because it connects several topics and concepts with what you have studied in your previous classes, including the algebraic expressions, polynomials, roots of polynomials, factorization, quadratic equations, etc. But you studied these concepts with regard to the real number systems in your previous classes. Now we will concept these topics, we will extend these topics within the purview of a set of complex number system. So you must recall what you learned in your earlier classes regarding these topics. So first of all, I would explain that what are the polynomials which cannot be factored over real numbers. So we take up the example of x square plus 4. So we will consider this polynomial, that whether it can be factored over the set of real numbers or otherwise. So the answer is no, because we will put this polynomial equal to 0 in order to factorize it. This implies x square is equal to minus 4 and x will be equal to plus minus 4 under root. So it will be written as minus 1 into 4 under root, and we will get plus minus 1 under root square root into 4 under root. We can write it as plus minus 2 iota, since iota is equal to minus 1 under root. So the solution of this equation, x square plus 4 equal to 0, or the solution of the polynomial x square plus 4 cannot be factored over the set of real numbers. It can be factored over the set of complex numbers. So over the real numbers, this polynomial is irreducible. This polynomial is irreducible over the set of real numbers. So this motivates our present topic, that there are some sort of polynomials which cannot be factored over the set of real numbers, and they can be factored over the set of complex numbers. So a complex polynomial we denote it as polynomial in Z is a polynomial function of the complex variable Z with complex coefficients. It can be expressed as polynomial of degree n in Z. Usually we omit this n, we do not write it in usual circumstances. It is equal to a n z raised to power n plus a n minus 1 z n minus 1, so on up to a1 z1 plus a0 z0, where an minus 1 so on up to a1 a0 are complex numbers with a n not equal to 0 and n is greater or equal to 0. Degree of polynomial. N is representing the degree of polynomial in this case. So we will discuss this concept to further the applicability and related concepts of linear complex polynomial, quadratic complex polynomial, cubic complex polynomial, and constant polynomial. So I would explain all these things with the help of examples. So let us take the example of linear polynomial. Linear complex polynomial. Linear complex polynomial having degree 1. I am writing in the brackets, degree will be 1. Degree is the highest power of the variable involved. So we write polynomial in Z with a degree 1 is equal to, for example, 1 minus iota into Z plus 3 iota. This is an example of linear complex polynomial. So we discuss quadratic complex polynomial. I am writing in brackets, it has degree 2. I take up the example polynomial function in Z of degree 2 will be equal to 5 minus 4 iota into Z square plus 2 plus iota into Z plus 3 minus 4 iota. So this is an example of quadratic complex polynomial because the highest power of the variable involved is 2. The variable involved is Z. So highest power is 2. So it is second degree complex polynomial, and second degree complex polynomial is also called quadratic complex polynomial. Similarly, the cubic complex polynomial we can write it as, I am writing in brackets that it has degree 3. So we can write polynomial function in Z of degree 3 equal to for example 2 minus iota Z cube plus 2 iota Z square plus 4 iota Z plus 3 iota. For example, this is a complex polynomial of degree 3 because highest power of Z here is 3. So this is called cubic complex polynomial. Now in case n is equal to 0, if n is equal to 0, then polynomial of Z is equal to constant polynomial. Constant polynomial we write it as polynomial in Z0 equal to 0. This is called constant polynomial. So you should keep in mind that fundamental property of complex polynomial is that they can be further factored into a product of linear factors. Similarly, as we did with the algebraic expressions over the set of within the purview of real numbers. Similarly, we will sort out the topic in solution of the questions in exercise 1.3. The remaining concepts I think are related, are not so important that we should discuss over here. I think that can be completely described during the solution of exercise questions. So I am omitting these concepts to be discussed here in the preliminary discussion of the theoretical concepts before exercise 1.3. Another thing which is we should reiterate is the fundamental theorem of algebra. A polynomial having degree n has exactly n roots of the complex number system. In the algebraic system we have studied कि किसी भी पॉलिनोमियल की जितनी डिग्री होती है उतने ही उसके रूट्स हासिल होते हैं. सिमिलरली द केस अप्लाइज विद इन द प्रीव्यू ऑफ सेट ऑफ कॉम्प्लेक्स नंबर्स. सेट ऑफ कॉम्प्लेक्स नंबर में भी ऐसे ही होगा, जितनी किसी भी पॉलिनोमियल की डिग्री होगी उतने ही उसके रूट्स हासिल होंगे. तो सारी चीज़ें चूँकि जो हम पहले विद इन प्रीव्यू ऑफ रियल नंबर्स पढ़ चुके हैं, वो हम सारी की सारी चीज़ें अब विद इन प्रीव्यू ऑफ सेट ऑफ कॉम्प्लेक्स नंबर्स पढ़ेंगे.